So the title of my slideshow is Tutorial Introduction to Containers for Scientific Container Native Workflows, featuring Charliecloud on ACEs. As I said before, we're going to be teaching some concepts of containers, but we're going to be focusing on getting you as close as possible to ready to do your research. I plan to have another short course in a few weeks where I dig deeper into the nuts and bolts of containers. If you want a more thorough understanding of containers, you can come back and join us in a couple weeks for that information. Today, we're going to start with a very short overview of containers, a very short overview of Charliecloud, and we're going to jump right into getting started. We need as much time as possible for doing our exercises so that we can master the skills we need to do research. We're going to be looking at scientific container image sources. We're going to learn how to work with images, work with containers, and then we're going to take a look at some example scientific use cases on the ACEs cluster. We have 3 prepared for you today: TensorFlow, LAMMPS, and Clara Parabricks, representing a wide variety of research fields. But as we'll see, they all rely on similar foundational skills of using containers. So the next slide is learning resources. We have many learning resources here at HPRC. The one that we're going to be using the most today are these slides. Actually, I think it's important for you to have a copy of these slides because we're going to be doing a lot of coding, and it can be a hassle to type each command if you don't get it right on the first try. So being able to copy and paste the command from the slides into your terminal could help you get past some exercise that's giving you trouble. So I'd like to take a moment to actually do that. So if we navigate to this website, hprc.tamu.edu/training/acescontainers.html, I'll actually put that URL in the Zoom chat. If we go to this website, you can see that there's a bullet here for the Charliecloud tutorial in fall 2023. That's this one. And there's a PDF. Please do open the PDF and keep it open in a tab or download it to your desktop, however you prefer to interact with PDFs. Because as we go through, there will be lines of code you may want to copy and paste into your terminal. And you can follow along with me. You can see these are the same slides I'm showing. Is everybody able to get to this PDF by navigating to the website? I can also put the link to the PDF directly. That's just an ordinary link in case the website is not loading for you. You can try getting to the PDF directly. That's the most important part. So I'm trying to show the slides again. If I go to full screen, does it stop working? Are you still able to see the slides if I'm in full screen? Okay, thank you for responding. I do appreciate your responses. Let's learn about containers. So I assume that you may have never seen a container before. So I'm going to give you the very briefest overview, a light concept of what is containers. What are containers? A container is a process that has its own view of local resources. There's some dispute about the definition of the word container. It can be used for multiple things. I'm going with Charliecloud's definition of a container because if you go to read the Charliecloud documentation, I want you to get a consistent understanding and not feel confused. So according to Charliecloud, a container is a process, and I'm using a gear here to represent process in the diagram I'll show you. So local resources include file system, user IDs, the network. There are many other resources. For today, we're going to be focusing on the file system resource. So if you have a process, a normal process sees a physical file system. Here I'm using the gear to represent a process and the disk to represent the physical file system. Now, somewhere on that file system, you may have a sector that contains the data of a smaller file system. So a smaller file system within a bigger one is called an image. It's a concept that we borrowed from back when file systems were literally on disks and they were optical. So an image was a representation of data. We use that same language here. So an image is a section of a file system that is a representation of another file system. So a container is a process that sees that image as the file system. It doesn't see the physical file system. It sees the image as though the image were the real physical file system. So trying to simplify the concept of what is a container, how is a container different from normal processes? Are there any questions about this slide? Let's move on. Why use containers? Containers are shareable. You can share your container image by uploading it to a public repository. You can use images that were shared by others. Containers are portable. You can use images on any computer with the same architecture. So architecture would be, for example, x84-64. There are two main architectures. There's like the one by Intel and the one by AMD. And so basically any machines that are using the same architecture. Did I say that wrong? I can never remember what the other architecture is. If someone's an architecture expert, go ahead and put in the chat what you think the two main architectures are. But basically, here at HPRC, we're using almost exclusively x84-64, so all of our containers work together. ARM, yes, Janel figured it out. I always get confused about what that other architecture is. And finally, reproducibility. Because this is a presentation for scientific workflows, I assume you want to do science. And one of the principles of science is that people should be able to reproduce your work at a later time. So if you are doing your work in a cluster environment that you're not actually in control of, somebody could change that cluster environment and make it not possible for you to reproduce your work. Putting your work in a container means that you're largely unaffected by changes to the cluster environment. As long as the cluster stays the same architecture, the container should have the same behavior. So that allows you to feel confident that your work is reproducible. So what goes in container images? A related topic that also uses images is called a virtual machine. In a virtual machine, you put the entire file system and an operating system in the image. So then you need what's called a virtual machine manager to emulate the hardware so that that guest operating system can function as though it were a whole operating system. So now you have two operating systems in the virtual machine setup. The downside of that is because the guest operating system is large, it takes up a lot of space in memory to run this thing. So you can only have like one or two virtual machines running at a time before you start running out of memory. In the container has a principle of being minimal. We do not replicate the operating system. Instead, we rely on the host operating system to do what it does. And the container runtime translates between the libraries and binaries in the container and the host operating system. This works because most of the flavors of Linux actually use the same kernel. So they can all like be swapped out on top of each other. So the blue part is the Linux kernel, that all the Linux operating systems have in common. And the green part is what makes one distribution different from another. So we only need the part that makes your distribution different from another. We don't need the part that they all have in common. And that means that containers are much smaller in memory, so you can have a lot more of them without worrying about running out of resources. Here are some popular container runtimes. Maybe you've heard of some of these. Containers have been around for a while, actually. The first functional container was LXC, all the way back in 2008. But aside from some extreme nerds, nobody really knew about it. The first container runtime to go viral, as they say, is Docker in 2013. Docker became extremely popular and was used by a wide variety of researchers in different fields. But Docker is not perfect. It has some problems. So to address those problems, a bunch of new runtimes have been created with different features that hopefully address the problems that Docker had. We have Singularity in 2015, which we still use, Shifter in 2016, Charliecloud in 2017, that's the one we're studying today, Podman in 2018, another new one that I do recommend, but for a different purpose. All of these containers are specialized for different purposes. And because we're going to be doing HPC things today on the ACES cluster, we need Charliecloud in particular, which is the best for that purpose. So let's talk more about Charliecloud. Charliecloud is a lightweight, fully unprivileged container solution presented by Los Alamos National Laboratory. The word Charliecloud actually comes from the original creator of the software. His name was Charlie, apparently. So what are some Charliecloud features? Charliecloud is both a container runtime and an image builder. That's huge because a lot of the other container runtimes just do one thing. But on HPC, you need to be able to do all your work on the same cluster. And Charliecloud enables that. Charliecloud can read and convert Docker images. So images that are in the Docker format, because they were created by someone who previously used another runtime, can still share with you because Charliecloud understands that common format. The file system inside the container is isolated. So other users can't see what files you have, and you can't accidentally break the host operating system when you're handling files inside your container. The user inside the container is isolated. So if you need to do special user things like sudo install Python, you can do that inside the container, but it doesn't affect anything outside the container, which is good because we can't give you sudo privileges outside the container. Charliecloud works with high-performance cluster technologies. So we have some demonstrations later where we show Charliecloud working with high-end technologies such as InfiniBand and NVIDIA GPUs. Because Charliecloud is lightweight, it does its best to simply let you use the hardware that's there. It doesn't try to emulate different hardware. So the high performance cluster technologies, the reason to be on a cluster like ACES, are supported. You can read more about Charliecloud. Oh my goodness. You can read more about Charliecloud on their manual, which is on GitHub, hpcgithub.io, Charliecloud. I do highly recommend it. They have a 90-second tutorial that I think is very high quality. So using Charliecloud on ACES, there are a few specific things you need to know if you're going to do container tasks on the ACES cluster. So first of all, Charliecloud is available from our module system. Our module system is lmod, so you type module load and then the name of some software. So our software is just named Charliecloud, so you do module load Charliecloud and you get access to our software. Charliecloud images, actually any images, can be large on disk. You're going to potentially install the libraries of a Linux distribution plus lots of scientific software. So you need to be aware of your storage quota. And in particular, the home file system on ACES has a smaller quota. So we're primarily going to be putting these large files in the Scratch file system where you have a larger quota. Some container activities may be too CPU intense for the shared login node. That's actually not a container specific concept, but if you're doing scientific tasks or if you're building software, you need to be aware of how much the CPUs you're using. And if you are going to be using a lot of CPUs, then it's better to use a compute node so we don't accidentally take down the shared login node and ruin the day for everyone else. And finally, some container activities may be too I/O intense for the shared network file system. Network file systems, while they do their best, they can struggle to keep up with a lot of users who are doing file input-output. So if you're doing a container activity that does have a lot of file input-output, then it's better to use a local file system to do those large image operations and then move your result over to the shared network file system after you're done with that heavy traffic. And I will show you how to do all of these things in our workflow strategy as we go forward. It's time to get started. How much time has elapsed? Good question. It's been about 25 minutes, and now we are ready to do our first activities. Everybody ready to do activities? The first activity is you need to get connected to the ACES cluster. So we connect to the ACES cluster using the ACES portal. That means you need an ACES account. So the link to the ACES portal you can find on our webpage. If you go to hprc.tamu.edu, we have a nice little drop-down menu portal, and the bottom option is the ACES portal. So you click on that and it takes you to your login page for ACES. If you do not like the menu option, you can, of course, type the URL for the ACES portal directly, which I have just dropped into the Zoom chat, so you can click on that. What is the ACES portal? The ACES portal is powered by Open On Demand. Open On Demand is a common high-performance technology for access users to get access to different clusters around the nation in your browser. That's more convenient than having to do things like get on your command line and type SSH from your home terminal. And the common interface means that as you move from one cluster to another, things should be easy to pick up and learn the differences. So Janel asks, do you need a VPN? You should not need a VPN. The ACES portal is outside of Texas A&M's firewall. For example, I can get to it on my phone as I'm driving down the road. So I think you should not need a VPN. Now, if you are in a restricted area of your own institution, you might need to change something about your own institution's VPN in order to get out. We have seen some problems. For example, our colleagues at Los Alamos National Labs by default are on a VPN, and they need to turn it off to get to the ACES cluster. So this is what the authentication looks like for access users. In case you're not super familiar with it, first you have to select your identity provider. So if you previously used Exceed, you may have an access ID that just is an ordinary username and password. But if you're newer to join Access, then you had the option to register using your institution credentials, which I do recommend because it's very convenient. And in that case, you have to select your institution from the drop-down menu. Then it will redirect you to your institution's authentication instead of the Access CI authentication. But in either case, after you successfully authenticate and complete your two-factor, you will be able to land on the ACES homepage, which has the ACES logo. So Once you have logged into the ACES portal, the first thing we need to do is we need to get a terminal because we're going to be doing some command line activities today. So you get to a terminal from the clusters menu. The only option in the clusters menu is the ACES shell access right now. So please click on that. And it should take you to a terminal in a browser tab. You can see my terminal displays the message of the day. And then we have the little $sign at the bottom to let you know that this is a bash terminal. I think your default will be bash unless you change it for some reason. So we need to execute some commands to set up an environment for today's activities. Not too complicated, but if you misspell them, you're going to have trouble later. So that's why I suggested getting your PDF, and you can scroll down to set up your environment and then start copying and pasting these commands so you know you've spelled them correctly. So for example, I'm going to follow along. So I have my terminal, I have my PDF with the commands, so I'm going to copy and paste these out of here. I have to click allow to let pasting happen, but other than that, other than the first time you click allow, copy and paste should just work with your normal operating system hotkeys. Like I'm on Linux right now, but it's Control-C, Control-V. So CD $scratch takes you to your Scratch directory. mkdir ch_tutorial takes you, oh, I already have one of those. CD will move you into that directory. pwd will let you know where you are. So I am now in Scratch user, my username, all your ACES usernames are going to look silly like that, /ch_tutorial. We just need something to put somewhere to put our files. So we're going to be making some files today. And if you want to clean up later, it should be easy for you to just go wipe the whole directory. Don't want to make a mess in your personal Scratch area. So let's keep going. There is a training directory where we have some files. I like to give that directory a variable to refer to where it is. So later when I want to, I don't have to type that full path. So I have $training, which is just a shortcut for this path. Scratch training Charliecloud, and there are some files here. We'll be using some of these files today. And finally, we need to load the Charliecloud software. So module load Charliecloud. This is probably one of the ones you should type on your own. Module load Charliecloud. It's not so hard to spell, and it's good for your fingers to practice spelling it. And then module list. So these are just some ordinary lmod commands. Okay, so next on our slide, your first image. So Charliecloud provides a few executables. One of them is ch-image. So we're going to learn how to use that to get images. We're going to get our first image. So ch-image and then help to just make sure that that executable exists and check how to use it. So it says the usage is ch-image, lots and lots of options, and then command. And your command options are build, delete, import, list, pull, push, reset, undelete. Today we're going to be doing pull and list. So if I head on over to these slides, I can see we want to image pull Alma Linux 8. Let's copy it out of the presentation to make sure we spell it correctly. ch-image pull Alma Linux 8. Okay, and that was done. So that took just a few seconds. Alma Linux is not very big. You can see it's only about, it's a few megabytes. So Alma Linux is one of the smaller Linux distributions, so this doesn't take very long. Now we've done ch image pull Alma Linux, we would like to know what images exist. So let's do ch image list. And it says, I have Alma Linux 8, and because I was working on this earlier, I also have an Intel. We'll be doing that Intel one later. For now, you should just have Alma Linux 8 as an image that you have on disk. But where is it on disk? So by default, Charliecloud will create a personal, temporary, local image repository for storing your images. And its location is pointed to by this variable chimage storage. So let's investigate chimage storage. What is chimage storage? Tab autocomplete actually works. Isn't that cool? So it says it's tmp/myusername.ch. Okay. And what's there? We have some files, including an image directory. And in the image directory, we have Alma Linux 8. So there you go. Isn't that neat? Was everyone able to investigate the chimage storage directory to see that the Alma Linux 8 image is landed there? Okay, very good. I just love this part. Okay, so this is probably the most exciting slide in the whole slide deck. This is the Your First Container slide. If you're not very familiar with containers, this is gonna blow your mind. Okay, so first, we need to verify what the Linux distribution is on the login node where you are. And because this is a flavor of Red Hat, there is a Red Hat release file that tells you what the actual distribution version is. So we're going to use cat to see the contents of the Red Hat release file. So I go to my slides, I copy cat, etc. Red Hat release. I paste that in my terminal, and it says Red Hat Enterprise Linux Release 8.8 UTPA. Okay, we're running Red Hat 8 on our login nodes. So the Charliecloud provides another executable named chrun, which launches containers. Recall, according to Charliecloud's notation, a container is a process. So we need to launch a process. And the syntax is chrun, the name of the image, followed by the name of the executable that you wish to launch. We'll just launch a bash terminal. But the bash terminal, instead of being this one that sees the real physical file system, it will be a bash terminal that sees Alma Linux 8, the image, as its file system. So you can see my prompt has changed. It used to say URL, it used to say username at ACES login, and now it says bash 4.4. So my prompt changed. It's still a bash prompt, but something is different. And that's one of your clues that this process, this bash terminal, is not seeing the same file system. Okay, so if it's not seeing the same file system, you might get a different result for your looking at your files. So let's try that cat etc. Red Hat release again. Cat etc. Red Hat release. And now it says Alma Linux release 8.8 Sapphire Caracal. So the same path to file, etc. Red Hat release as we did before. But now, instead of seeing the file that's on the real physical file system, it sees the file that's in the Alma Linux 8 image, located at the same location, but it's a different file. We are currently reading slide 22 in the slide deck. Please do try this exercise and let me know if you were able to execute the bash terminal with the container and discover the Alma Linux release file, and let me know if it in fact did blow your mind. Okay, I'm assuming that you're not going to tell me it actually blew your mind, because how many people out there are excited about containers as I am? I don't know. So one more thing, you can see that I'm still in this bash terminal. This process is still running. If I want to stop the process, I just use the exit command, which is the standard exit command for any bash process to stop. And then it returns me to the previous terminal that I had back on the login node. And just in case you're not sure, yeah, we're definitely back on the login node. Did anyone want to do further investigations? Oh, by the way, congratulations! Welcome to containers. Pew, pew, pew. I think that once you have done first time seeing terminal in a container, it really changes your world. And I'm so excited for each and every one of you to join the wonderful world of containers. And that's why I made a whole slide just for this fireworks animation. Courtesy of funimata.com, apparently. So JRash asks when we're back on the login node. No, actually, we were on the same node the whole time. Recall from my earlier slide, come on, slide options. Where are my slides? Recall from my earlier slide, I said that with a virtual machine, the virtual machine manager emulates a hardware for a node, so the guest operating system thinks it's on a brand new node. With the container, we don't do that. It's the same hardware and the same operating system kernel. All that's different is the specific files that are in the container image, whichever ones they happen to be, and everything else is the same. So we are on the same node. How do we know we're on the same node? That is a good question. Let's go back into our container and find out. If you activate host name, it says alogin1.cluster. And if you are not in the container, it says alogin1.cluster. So both in and out of the container, the bash terminal agrees that the node is alogin1.cluster. It's the same node. And that's why containers are so much more lightweight than virtual machines, because we are not creating a new node, we're using the same node we had before. Sometimes when I say we're back on the login node, what I really meant is we're not in a container anymore, but because language is hard, I may say something that's not very helpful. Thank you for asking that question. So let's move on to container image sources. Where do container images come from? I'm going to pop into full screen for a bit because it's just going to be a few slides in a row. So Charliecloud is a kind of a newer player on the scene. Containers have been around for a while, so the most common repository where people are putting their containers is Docker Hub, as Docker was the first popular container runtime, so a lot of container images are just there. That's where they were. There are other repositories. We have a Singularity Hub and a Singularity Library. I think those are being shut down now that Singularity is moving to Apptainer, but I assume there will be some kind of Apptainer repository. We have the NVIDIA GPU Cloud, where NVIDIA publishes containers. Quay.io, it's kind of like Docker Hub, but with more developer tools in case you want to get really into making these images. And we have Biocontainers, which is a curated repository that's just for biologists. We have some examples on how to use these repositories in our Singularity documentation, because I wrote the Singularity documentation in the past, and so that's currently where these examples are described. But you can use all of these with Charliecloud as well. So let's take a look at Docker Hub. Is anyone here familiar with Docker Hub? Maybe you've previously used a different container runtime. If not, no big deal. We'll start from the beginning. So Docker Hub is a website. You can go there. You can search for images. The images are grouped together, similar to GitHub. So you have your group/name is where each repository is located. So on the example on the right, we have the Jupyter/SciPy notebook. So the group is Jupyter. So there's a whole bunch of people who make Jupyter images and they put them in here. And SciPy notebook is the name of this particular repository of images. So all the images in this repository should have SciPy and Jupyter notebook installed in them. And finally, each individual image has a tag that describes how and when it was built. Latest is a tag that is like a symbolic link to whatever the most recent tag is, or you can specify a specific tag. So you could specify this Ubuntu 22.04 tag, which says the image was built on top of this particular distribution of Linux. But if you just specify the latest tag, you'll get whatever you get. Normally, I don't like to specify latest, but it is easy, so we're going to do it today. When you wish to pull an image from the internet, normally you need to specify a URL of where on the internet this repository is found. So it would be URL/group/name, and then if there's a tag, you go :tag. But because Docker Hub is the default repository in Charliecloud, you don't need the URL if it's just Docker Hub. So then you would just go group name tag. So therefore, the pull command for this example is chimage pull Jupyter/SciPy notebook :latest. And we'll actually do that one soon. When? I don't remember. Is it now? No, it's not now. We'll look at another example. So Clara Parabricks is a biology pipeline, and NVIDIA has produced a build of it that runs on NVIDIA GPUs. And you can see here in their performance comparison, they say, oh, if you use the CPU, it will take you this long. And if you use our GPUs, it will take you this long. So clearly, if you're a biologist, you are well motivated to learn how to do that and save some time. So where do you go if you want to get NVIDIA's build of Clara Parabricks? You go to the NVIDIA container registry, which is NGC. I don't remember what it stands for. So NVIDIA has a subdomain for their HPC, what do you call them? HPC images, and it's the URL is nvcr.io/NVIDIA. That's the domain for where they put their images. And then the images also have a group and a name. So there's a Clara group and a Clara Parabricks repository, and it has a tag for 121 in this screenshot. Now that is a lot to type in. So instead of typing it in, here's a quick trick. You can click a button on that web page, and then there's a copy button where you can copy the path into your clipboard. So you can paste the path directly onto your terminal. So you don't need to type all those letters accurately every single time. You can just go browse the internet, copy the whole entire link, including the URL. Working with images. So there are two main formats for images. We have a directory format, which is similar to how files are stored in the real physical file system. You just have a real physical directory that represents the image's root directory. So all of the files are relative to the root of the image's directory. And then in the second example, you can bundle up the entire file system into a single file. And for that purpose, HPRC supports the SquashFS file system format for single file images. We'll talk more about that file format on a later slide. Now, first we need to learn how the tool works that copies images into different formats. So we have the chconvert tool. If you're curious, you can do chconvert space -- help to learn how it works. So first we'll talk about the directory image format. If the image is in a directory format, then its name ends in a slash. That's the clue to Charliecloud that you want that image to be in the directory format. Directory images are writable, so that's the advantage of being able to use Charliecloud with directory images, is that you can modify your images. They are writable. However, because Linux distributions tend to have like many thousands of files in their directory tree, reading and writing all of those many thousands of files is very slow. So if we try to do that over a network file system, it's going to be like literally 10 times slower, and it's going to make it so that everyone else is having to wait to do their input-output operations. So instead of using the network file system, we're going to use the high-speed temp file system. Recall earlier we saw that the image storage pointed to a location in the temp file system. So that would be a reason why that is the case. The images that are in the temp file system are also directory format images, but when you're referring to those, you don't use the trailing slash. If you don't put a trailing slash, then Charliecloud understands you mean an image that's in your image storage repository. If you do put the slash, then you mean a literal path on disk to an image in a directory format. So let's do an example with our example repository from our previous slide, the Jupyter SciPy Notebook latest image. Oh, did I forget a step? I don't know what happened. I meant to have a slide where we actually do the ch pull. What happened to it? Oh, okay. It was this slide. So on this slide, it was an exercise. Do you see the word exercise up here? I forgot to read the word exercise, and I forgot to ask you to do this. We do need to do this because we're going to be using the image. So let's head on over to our slides. Image pull Jupyter SciPy Notebook latest. If you don't want to type that all in, you can copy and paste it into your browser, terminal. It is a little bit bigger than Alma Linux because there's some software installed in there. It's got like Python and Jupyter and some Python packages. So this one takes more than a few seconds. I think this one takes like a minute, maybe 30 seconds, something like that. I was supposed to ask you to do this earlier, but I forgot to. So now we all have to wait. Please do execute the image pull And then we'll all wait a minute for that to finish so we can go to the next step. Alex asks, if you unload the Charliecloud module, will your image be gone? No, your image will not be gone. Your image is on the temp file system. And while the temp file system has a lifetime of like, I think it's weeks or something. Eventually the sysadmins come through and clean it up, but they don't do it continuously. Unloading the Charliecloud module will cause the CH image storage variable to disappear, but that's just a variable that points to a location. The actual location on disk will still be there for the next time you load. However, that location on disk is node specific. So if you end up logging into a different node, you can see I landed on login node 1. So if you go to login again and you land on a different login node, your image repository on that login node will be empty because the repositories are node specific, because they live in the temp file system, and the temp file system is specific to each node. That's why it's a high-speed file system, not a network file system. So if you log in again and you don't have your image, you can either keep logging in until you get to the same node, or you can just pull the image again. Either one's fine. So I believe everyone had a chance to pull this image. And then we were going to learn how to use chconvert. So we learned what a directory image is. Okay. So that means we want to convert the image we just pulled into a directory format image. I'd like to make sure that I still have my image. Okay, so if I go ch image list, you can see I do have a Jupyter SciPy notebook latest. Okay, so the instructions say we need to make a directory in the temp space where we're going to put this image. We can't reuse the image cache. If you put an image in the image cache, Charliecloud will complain that it doesn't belong there. So we need to make a new space. So just go ahead and make a space for yourself in the temp file system. For example, you could name it your username. That's what I'm suggesting here. So if we scroll down to slide 34, you can say make dir temp user. Everybody's allowed to use the temp file system on the login node. Just be respectful to the other users. And then I want to see that my directory is there. Okay, temp and then my username. So that's a space that is for me, and you need to make a space that's for you, and then we can use it. The instructions say, let's do chconvert. So the syntax is chconvert space, the name of an image. In this case, we're providing the name of an image that is in your local image storage, so you don't need the slash. No slash means go to the image storage and grab one from there. And then the second argument is the location where you would like the copy of the image to go. So we would like it to be located at temp, your temp directory, and then you give it a name. You don't have to give it the same name. So I named mine Jupyter because it's just easier. I just don't want to type so many characters. And then it has to end in a slash because that's your clue to Charliecloud that you would like the image to be in a directory format. So let's copy this line of code, paste it here. And that only took a few seconds. Recall that moving thousands of files around is no big deal on the local high-speed temp file system. That's what we learned from my earlier slide. So now if we investigate again, you can see that now there is a directory named Jupyter in my temporary folder. And that directory is in fact an image in the directory format. Is there anything in the image? That's a good question. Yeah, so you should recognize these as normal looking Linux directories from the root. So for example, if I look at the root directory of the login node, I see similar looking directories. They're not identical, but they're similar. So what's inside the Jupyter directory is the root of a Linux distribution, similar to the root of the Linux distribution in the real physical file system. Has everybody had a chance to make that? We do need it for some exercises, so please do follow along. Let's learn how to edit the images. I told you that directory format images are writable. All you need to do is add the write flag when you run a process out of that container, and then any changes that process makes will be saved in the image. So let's get a bash terminal in the image, but instead of providing the image name from the cache, we're going to provide the path to this particular directory image. We're going to add the write flag. Oops, I forgot. I have to copy out of this one, the one that's not in presentation mode. So I'm going chrun write, the location where we put our directory format image, bash. Bash is the name of the process I want to launch. So now I have a bash terminal that is running out of the image. And yes, you can run containers out of directory format images, but it is a bit slower because there's lots of files instead of one file. So this isn't great for performance, but it is great for just making some quick little changes. So now that I see, which file system do I see? This, it's hard to tell, but this is a match for the file system that's in the image. If you recall, in the image, there was no ADM directory at root, but in the real physical file system there was. But now that I'm in the container, there's no ADM directory. So this container sees the image as its real file system. So now if we do, oops, that wasn't what I meant to do. Now if we make a scratch directory, you can see that the scratch directory now exists in this container's root area. Are there any questions about how I made that scratch directory? You might be asking, but wait a minute, isn't root directory location owned by the root user? How are you able to just make directories? Good question. Actually, when you're in a Charliecloud container, all the files are owned by whoever you want. In this case, they're just owned by me. You can actually specify that. There's command line options. We're not going to learn them today. But if you don't specify anything, the files are just owned by you. So no big deal. You can go ahead and make edits to the root file system in the container. So now we've done that. We've done make dir scratch. We want to exit the container. Just to check, did I harm the real scratch directory? It says the real scratch directory is owned by root and it was last created on May 2nd. So no, the one that I created is today, September 22nd. The real one is May 2nd. So I didn't touch the real one. The real one was not affected by this. Now I said that the changes are saved. So if we go back into our container and look around, we see that the scratch directory is still there. That's important because if we can't make permanent changes to these containers, modifying them is really of no use. Let's learn about the SquashFS image format. The SquashFS image format is an open source file system format for file system images. And in the SquashFS image format, the whole file system becomes one single file. The file name should end in .sqfs, which is short for SquashFS. That's your hint to Charliecloud that you would like it to use this file format. The downside of a single file image is that it's read-only. You cannot easily modify the contents of a single file. The advantage of the single file is that it's very fast to read from it, even over network file systems. So it's perfectly safe to put your SquashFS files in the network file system Scratch. So we're going to do that. Make sure you're still in your CH tutorial directory in Scratch area. PWD to make sure you're in your Scratch area. Recall, these images are large enough to affect your quota, so we don't want to put them in your home directory or somewhere else where we might ruin your quota. So you want to put them in your Scratch directory. PWD. Oh, that's right. I forgot. I'm still in the container. Exit to leave the container. PWD. Okay, so I'm not in a container, and I am in my personal Scratch directory in the CH tutorial space, right? Now we need to do page 37, CH convert. CH convert again, but this time first is the source image. The source image is that directory format image we were playing with. And the destination image is anything ending in .sqfs. So I named mine Jupiter, because you can name it what you want. It's just an ordinary file. CH convert from directory to SquashFS. CSS says parallel make SquashFS using 96 processors. That's not great for a login node. If this was going to take a while, then using all the cores on the login node for a while would be really inconsiderate. Thankfully, this is a small enough operation that only took a few seconds. So I haven't actually ruined everyone's day on that login node. If you were doing a CH convert that was going to take longer, you should probably do it on a compute node for that reason. But for this one, we're okay. And then, so where did that file go? Well, it's here. There was already some files here because I was using this directory earlier. But you can see this Jupiter.sqfs file is from today. So that one's just been created. So please do create the Jupiter.sqfs file. And then we should check to see that our changes are still there. Remember, we made a Scratch directory, mkdir Scratch. We should check to see if the Scratch directory is still present in there. Chrun Jupiter.sqfs. The syntax is chrun name of image followed by what command you want to run. I'd like to run bash and ls. And let's see, yep, there's the Scratch directory, it's still there. So now we can make images in different formats that preserve our changes. And then after you've checked that your Scratch directory in the Jupiter SquashFS does exist, you can exit the container, because the next example, we're going to do something a little different. So that's enough for learning about working with images right now. We've learned how to modify an image. We've learned how to convert an image from one format to another. And we've learned which file system you should be keeping your images on. Next, let's learn what we can do with these images. So far, all we've done is launch bash terminals and poke around. Feel free to launch bash terminals and poke around as you wish. Obviously, you can have a lot of fun in inspecting these containers, but we're here to do scientific things. So let's learn how to do scientific things. So the first thing you want to do is you want to be able to mount files that are outside the container to inside the container, because containers are mainly used for software. If you're going to be processing data, you should not be keeping data in your container, because then every time you execute your container, the container would have to change, and then it would be slow. You want your container to be mostly static. So if you're just working with data, your data should live outside the container. So that's why we have this concept of mounting. So if we mount the real physical scratch space to inside the container, then when you're running your container, you can have access to all your normal files. So how do we do that? We have the -B option, which says, take this scratch. If you just provide the path to a directory, what it means is make the path inside the container image, that is this one, be like a symbolic link to the same directory location outside the image. So we have an empty scratch directory in the container. We're going to overwrite that empty scratch directory by making it into the real actual scratch directory outside the image. So that's what -B here is doing. Now you can select for the interior and exterior directories to be different. You would just use a colon, but we don't need that for this example. Then the next option is the -C option, which we use to set the starting working directory in the container. So every time we've launched a container, we've started in the root directory. It's not convenient to start in the root directory, so let's start in our personal scratch directory instead. So you do -C and then you put scratch, and it will start you in your personal scratch directory. And then of course we're just going to run a terminal right now because we want to see if the files are correctly there. So chrun -B/scratch -C $scratch. And now we have a terminal. If I do pwd, you can see that in the container, my current location is scratch user, my username, and my files are there. These are my actual files that are actually on disk in the real physical file system. But I'm in the container. So in the container, part of the real physical file system is still accessible. How about that? So now if I have some data in my scratch file area, I can access it from inside the container. I can read and write to it, no problem. So I don't have to continuously update the container every time I have new data to work with. I will now exit my container. Let's do the next topic. The next topic is working with variables. Some containers come with environment variables that are needed in order for the application to function properly. The --setenv option is used to turn those on. So for example, this Jupyter image that we downloaded from the internet has some environment variables in it that need to be set in order for the software to function properly. By default, Charliecloud does not set any of those variables, but you can easily do it just by adding this option that says Charliecloud, please do set those variables. I'm going to use my copy. Chrun --set setenv space name of image name of executable. So for this example, we want to launch Python. Now, Python is one of those programs that needs environment variables in order to function properly. So if you try to execute Python without the setenv, it's not going to work. In fact, I'll show you live. It says, I don't even know what Python is. But when we add the setenv, now it creates those variables, and now Python is functioning properly. It says Python 3.11 was packaged by Conda. Does it have any packages? If you're familiar with Python, you may recognize NumPy as a commonly used Python package, and you can see it's installed here in this conda space. Conda is not the default area for executables, which is why we weren't able to find the executables without the help from the environment variables. So I use exit with the parentheses to leave Python. Remember, the exit function in Python requires parentheses to function properly. And now I'm no longer in the container. Because I never launched a bash shell, when I exit Python, there's no bash shell in the container to drop back into. So I just go straight back out of the container. The particular variable that is making it possible for Python to find NumPy is named Python path. So that is one of the variables that is in the container that is used to make this work. Let's do something fun. So let's do an interactive graphical computing. So you probably still have your ACES portal open. So if you go back to your ACES portal and you look at the interactive apps tab, you'll see that there's a Jupyter Notebook option. Is anyone here familiar with Jupyter Notebook or Google Colab, or is a Python programmer? If you're aware of these things, I'd like to know about it. For example, Jupyter Notebooks are very commonly used to develop machine learning applications. So if you want to do some development on the cluster in a Jupyter Notebook, no big deal. We got you covered. Good question. Nan and Shan says, is this using Python in the image or not? We can find out. So we saw that when we executed Python from the image, it was Python 3.11 packaged by Conda Forge. Whereas if I am not in the container, you can see my prompt is telling me I'm not in a container, and I try to execute Python, it says Python is not found. There is no default Python installed on this login node. We do, of course, have Python installed. It's just installed through the module system. You would have to do something like module load blah, 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 Python. And then you'd be able to do that. But by default, there's not one. So that's one of the ways we know this Python is running out of the image. You can install Python in your user space, or you can module load one of the Pythons we already have. There are many ways to get Python. I'm not trying to claim that containers are the only way to do Python. So if you click on Jupyter Notebook, please do follow along because this is fun. You'll see that we have Home, My Interactive Sessions, Jupyter Notebook, and you have a form to fill out. We just need a couple of options from the form. So first, you need to choose containers from type of environment. So as you click on containers, the form changes. Next, you need a path to a container image file. So scratch chtutorial jupyter.sqfs or wherever your file actually is. So if I go to my slides, I can copy this. Now, if you don't have this one, because maybe you weren't able to follow along, you can use the backup copy located in the Scratch training area. But I'm going to use this one because I do actually have one. So I'm going over here and I'm putting that in the path to container image file. And yes, it's okay to put variables. These variables will be expanded once the notebook actually tries to launch. So it's whatever is on the node where the Jupyter Notebook tries to launch. For example, the Scratch file system is what will be used to parse this variable, so it's fine. There's a note here that says Charliecloud images should have a Scratch directory. That's because when I created this app, I decided that I would like to be able to mount everybody's Scratch space. It's the most commonly mounted thing. And the way that I decided to do that is to mount it into the Scratch area. Maybe I'll change this, but for today, this is how this works. You can click a node type. I'm going to go with CPU only because I want this job to just launch quickly. And there's more CPU nodes than there are GPU nodes. and you can leave the rest of these on their default values. If you click GPU, you probably can get one. It'll just take longer. And then we have to click some buttons. So we click the launch button, and then you have to wait for your job to be ready. And then you click the connect to Jupyter button, and then you have to wait for Jupyter to be ready. And then you click the new notebook button, and you have to wait for your notebook to be ready. And then you can try out your Python. So we have this slide in the deck as well, if you're following along from the deck. So I hit the launch button. Any questions about how to fill in those fields, by the way? Most of those are Slurm parameters. Anybody here worked on a cluster with Slurm before? Familiar with things like memory and dwell time? Okay, my Jupyter is it connected to a node, so I can connect to Jupyter. And you can see that Jupyter is running in a space where my files exist. This happens to be my Scratch directory. And you can create a new notebook, or you can open a notebook you already have, if you somehow have one. And you can run your cells, and you can see that in my Jupyter notebook, I can import NumPy. NumPy is running out of that conda install. This is definitely the one in the image. How can we prove that? How can we prove that we could do something like this? Okay, that's just because I'm familiar with Jupyter Notebook. If you're not familiar with Jupyter Notebook, no big deal. This is just an example of containers are not just for the command line. If you like to develop your applications in a graphical environment, we can definitely support graphical environments that run out of containers. So you can see that I have a Jupyter notebook is still running. I forgot to make it not do that. So if you go into your My Interactive Sessions tab, which is this very small button with the two rectangles, that's how you get here. If it's still running, you probably want to turn it off because you don't want to waste those resources. So you can either do like file shutdown from the Jupyter tab, if you still have that open, or you can hit, and now it changed to completed in here, or you can hit delete in here, which will also kill the job. Just to be courteous to other users on the cluster and not leave our jobs running when we don't really need them. So the last topic is containerized scientific applications. The first scientific application we're going to look at is machine learning with TensorFlow. So where can we get an image with TensorFlow? There's lots of options. For this example, we're going to look at Intel's build of TensorFlow. Intel has built a version of TensorFlow that's optimized for Intel processors. So this is for CPU running. We do have Intel processors on the ACES cluster. This is not the most common use case because I would say probably most people doing machine learning with machine learning are probably using a different framework like PyTorch, and they're probably using an accelerator like a GPU. So Intel optimized TensorFlow is not really where it's at in 2023, but we already had the example, so we're just going to use the example we already had. So what do we need? We need an image from Docker Hub. So if you went to Docker Hub and searched Intel optimized TensorFlow, you might be able to find this repository. And so we're going to pull that image down. So if I go over to my containers PDF, I can copy the ch image pull Intel optimized TensorFlow AVX 512, and I can drop that into my terminal. If your terminal died, you'll need to do module load Charliecloud again, and make sure you're still in your Scratch area. Yep, I'm still in my Scratch area. So what the heck did I do? I lost my clipboard. Okay, so it says using existing file. That's because I downloaded this image earlier, and Charliecloud is smart enough to say, oh, I don't need to download that. I already downloaded that. So that's what the idea of a cache is. Charliecloud keeps track of things it's recently downloaded, so it doesn't have to download them again. If you're downloading this file from scratch, it will take a couple of minutes because it is not small. So if you would like some time to download this file, that's fine. We can wait. Maybe you're thinking TensorFlow is not for me. I'll just skip this exercise. That's fine too. I'm not here to tell you what to do with your time. Is anybody wanting some time to download this file? Okay, not seeing anyone asking for time. So if we do the ch convert, we want to turn this, what is this? Cache image. We want to turn this, what did I do? Oh my goodness. You have to copy the whole line, Richard, the whole entire line. So we want to copy this cache image and make it into a squashfs image because squashfs images are faster for reading and writing. And we want to do things on the cluster. We don't want to be wasting resources. And also we want a copy that's going to stick around. So this one is in our like temporary cache. We go to a different login node or a compute node, it won't be there. It's only on this login node. So, but if we convert it to squashfs and put it in Scratch, now it's on all the nodes because Scratch is a network file system. So if I hit ls, I can see I have Intel TensorFlow.sqfs, which is just what I chose to name this. It's a regular file, so you can name it whatever you want. And now this is on the Scratch area, so it's network file system. So this is now going to be usable on compute nodes or any nodes. And what can we do with TensorFlow? Well, TensorFlow is a Python framework, so we need to launch Python, and then we need to import TensorFlow to see if it's there. We've previously seen that there's no Python on this login node, so if I execute chrun Python, it's definitely not going to work. So being able to import TensorFlow means you're looking at a version of TensorFlow that is in the image. So for this particular build, we don't need the setenv, as it turns out, because Intel chose to put their Python executable in the standard area, the USR bin area. So we don't need to set any environment variables in order to correctly find that build of Python. Again, this varies depending on who built the image. One of the motifs is if you put garbage in an image, it's still garbage. The containers can't save you from garbage developers. But Intel knows what they're doing, so they put Python in the image in a standard place, so it's no big deal to use it. Good on you, Intel, for building a container image that's easy to use. Import TensorFlow as TF. That's standard practice in machine learning if you're into TensorFlow. I'm not telling you to use TensorFlow. I'm just giving you an example. And let's take a look at the version. So the syntax is tf.double_version. And it says 2.13.0. Very good. Now we know how to show that TensorFlow is installed. Where is it installed? It says it's installed in one of the standard locations, USR local lib. So that's why we were able to find it without setting any environment variables. And remember, the exit function has parentheses. So when you're done playing with Python, when you're done playing with Intel Python, just hit exit with the parentheses. Would anyone else like to take some time to play with this, or do you feel done playing with this one? You'll notice I did this one on the command line. it should be reasonable to do this from Jupyter Notebook. We're just not taking the time to do that at the moment. So let's talk about scientific application number 2, LAMPS. LAMPS is a molecular dynamics simulation that runs on GPUs. Lamps.org has a cool animated logo. I just can't resist showing you this animated logo. Look at that. When you hover your mouse over it, the molecules move. Look at that. That's just cool. Yuvaraj says syntax error. Can you show me what you typed that ended up with a syntax error? Is this one your syntax error? Chrun Intel TensorFlow. Change quotation marks. Is this your syntax error?
No, not that one. When I want to check like the version, it says. So this is like from the slide, I can paste it, right? Like print quotation TensorFlow version, that line.
Probably, yeah, it's probably due to the quotation marks. So you see, these are the like slanty quotation marks. Those are technically not considered quotation marks by Python. So you'll need to replace those with like regular quotation marks.
Okay, thank you.
That's just a consequence of like copying and pasting things. Unfortunately, sometimes it doesn't do what you want.
Thank you.
I want to talk about lamps. So we want to be able to simulate molecules using an NVIDIA GPU. Who better to build that software than NVIDIA themselves? So NVIDIA provides GPU-ready container images for lamps. We've seen an example. Let's take a closer look at this example. So here we have the NVIDIA GPU catalog or something, and it's got container images. So if we click over to tags, you have to find this specific build, patch_15 June 2023. Okay, that's the only one that will work for us today. If you find this specific build, and then you come over here and there's a copy to clipboard button, copied. So why type when you can copy? So much easier. So then we head back to our slides. Yeah, this is the slide. This specific build works with H100 GPUs. So you follow the link, or you search on their catalog for lamps. You click on the tags tab, and then you get the URL for this specific image. nvcr.io/hpc/lamps:patch_15 June 2023. And we need to fetch it, but we're not going to do that yet. We're going to do that on a compute node. So don't fetch it yet. That's not useful. In order to use GPUs with Charliecloud, we need to modify the container image. The build that NVIDIA produces is not complete. It's missing NVIDIA libraries. And the reason for that is you need to install NVIDIA libraries on your compute node. Those NVIDIA libraries have to be plugged into the local GPUs. So it's not good enough to put them in the container. They have to be on the node. So they're not in the container. So in order to use GPUs with Charliecloud, we need to put them in the container from the actual login node where they are found, from the actual compute node where they are found. And we need one other thing, which is called the NVIDIA run script. The NVIDIA run script is actually in the container. I just couldn't figure out a good way to get it out. So I have a copy for you. So we're just going to use the copy I made, and we're going to put that in the container image as well, so that it's in a location where we know where it is. In order to do the injection process, we need 2 tools. We need the NVIDIA container command line tool. We're not actually going to use it. It just needs to be installed. And we need the ch from host tool, which is a tool that helps you inject files into a container image. On ACES, NVIDIA Container CLI is provided as a module. So we're just going to have to load that module. Compute nodes with GPUs have the NVIDIA libraries installed, so the login nodes do not have them because the libraries have to be installed on nodes where they are GPUs because they're plugged into those specific GPUs. And we have a copy of the run script in training. So that means we have a couple of steps to do. The first step is get to a compute node. That means we need to use Slurm to get to a compute node. And for this example, we're going to use the srun command to ask Slurm for a compute node. Am I sharing my screen properly? Can you all see a slide that says get to a compute node? So this is slide 50. So you're definitely going to want to do copying and pasting because this is a lot of text. So I'm scrolling down to slide 50. Okay, so we have a reserved node for this activity. It's the node AC027. So in addition to all of those flags, we're going to add one more flag to get to this specific reserved node. You can see our H100 GPUs are very popular. Lots of people are using them in Slurm right now. So if you want to get to a GPU today, your best chance is to use our reserved node. So we're going to get to a compute node. We're going to copy all these flags into our terminal, and it has to be all on one line. So you copy the first line, space, copy the second line, oops, space, and then I'm going to add one more flag. I'm going to add the reservation equals short course. Did I spell that right? Yes. So I am now on AC027, which is our reserved node for the short course. So I'm going to copy and paste this text into the Zoom chat so you have it as well with the reservation. So in the Zoom chat, I'm pasting the text. Remember, when you copy and paste out of the Zoom chat, you have to make sure it goes all on one line. It's probably not going to do that. So I would copy it like a little bit at a time to make sure it's all on one line in your terminal. I'm actually going to exit this compute node so that other people can use it. There are four H100s on the node. So if you don't get lucky and land on a GPU node that's available, then you can use one of those. But I will not, so that other people have a chance to use it. So we do this to get to a compute node. How do you know if you're on a compute node? Type the hostname command. It should come back as like AC0 and then some numbers. Does it have GPUs? Type NVIDIA SMI. If you're on a login node, hostname login, NVIDIA SMI, it says it couldn't do that because there's no NVIDIA driver. The NVIDIA drivers are the thing that are installed on the compute nodes. So if your NVIDIA SMI does something useful, you know you're on a compute node that has graphics cards. We want the H100s because those are the spicy new toy. Everyone wants the H100s. They're very new. So once you are successfully definitely on a compute node, you have to set up your environment again. So you won't be in your Scratch directory. You'll probably be back in your home directory. So you need to go CD Scratch back into your Scratch directory. And then you need to load your modules again because they will have been unloaded. Module load, Charliecloud, NVIDIA, container CLI, and web proxy. Web proxy is needed to get to the internet to pull the image. We have to pull the image on the compute node because we have to manipulate it on the compute node. Web proxy is how the compute node is going to get access to the internet. It's one of our modules. So copy and paste those commands back into your terminal. cd scratch ch underscore tutorial. Module load Charliecloud NVIDIA container CLI web proxy. So as you can see, there's no output from those commands, but if you hit it with module list, you should see the NVIDIA container CLI and the web proxy are now loaded modules. Is everybody able to get to a compute node and load those modules? Okay, if you're not interested, you can just hang out back and listen, but I do want the people who want to try the GPU exercise to have a chance to try it, okay? The purpose of web proxy is to enable the compute node to reach the internet. Compute nodes on ACES by default are not connected to the internet, but we can use a proxy to get them to the internet. That's what the web proxy module does. It just sets the correct environment variables for a proxy so that the compute node can get to the internet. We need to get to the internet so we can pull that NVIDIA image that we previously identified. We need to pull it onto the compute node because we need to modify it on the compute node. If we try to do this on the login node, then you'll realize that something is missing and you'll have to start over. So no point starting over. Once you're on the compute node, we can build our GPU-ready image. You probably want to do copying and pasting from the slides because there are several commands here. I will talk about them while you're doing them. I can't do these because I'm not on the compute node. I left the compute node to make sure other people would be able to use it. I guess in the meantime, I can just talk about these commands. So the first command should look pretty normal. chimage pull. We've already learned that can grab container images from the internet. And then here's that URL we found from the NVIDIA catalog. Copy, paste. And then once you hit that, it will take a moment because it's one of the larger images. The next command is something that will look familiar, convert, and then we're converting the image from its in the cache format to a directory format. Oh, did I make a mistake? I think this has to end in a slash. I said it had to end in a slash, right? And tmpdir is a location in temp that's specific to compute nodes. And then ch from host is a command that can inject files. So I guess we didn't need the slash for this case for some reason. I thought you would need the slash. ch from host is a tool that can inject files. If you go -- NVIDIA, it searches for the NVIDIA drivers, finds them because you're on a compute node, and puts them into the image. The image is the other argument. Then we have to do it again. ch from host. D means we're going to put something in the root of the D is for destination. Slash means the root. We're going to put something in the root location. What are we going to put? We're going to put something that's at the P for path training run script. So I said we have a copy of the run script at training. We're just going to put it in at the root directory so we know exactly where it is. And where are we going? Which image we're going to put it in the lamps image. And then finally, the image is now GPU ready, so you want to convert it to lamps.sqfs, a single file image in your scratch area, so that it's on the network file system, so it'll be available to every node. And this will also take a moment because it's not a very small image. Does anybody want some time to build that image? There's several commands here to copy and paste. But does anybody want time to find a GPU node that didn't get a chance to get on a GPU node yet?
I was able to build it and run it. Got lucky, but I still have a question. Can you go back to the previous slide? So ch dash from host dash dash NVIDIA.
Yeah.
What this command is doing? You said this is injecting a file, but what file is injecting into the image?
So if we go back a couple, it says tools needed. We need the NVIDIA Container CLI tool.
Yes.
NVIDIA Container CLI tool, basically what it does is it prints a list of all of the files that are needed for drivers and such. So the NVIDIA Container CLI basically prints out a list of all the files that are on this machine that are part of the NVIDIA drivers. And Charliecloud uses that tool when you provide dash dash NVIDIA. What it does is it says dash dash NVIDIA, okay, I'm going to try to use this tool. Do we have it? Yes, we have it because we loaded it. And then the tool spits out a list of all the files. And then one at a time, it takes all those files and copies them into the image. That's why it's important that we provide the CLI tool so that Charliecloud knows where the files are it needs to inject. Did that answer the question?
Yeah, and the next command is like the previous one. You are mounting something from outside the container to inside the container, right?
Right. But instead of, so a mount is temporary. A mount only happens during running a container. This is a permanent copy, but the syntax is similar. It's bring from outside to inside. For some reason, I had to write it backwards. I had to write outside first, inside second. That's a bit weird. I filed a bug report with Charliecloud that says, hey, Charliecloud, why do I have to put outside first, inside second? But anyway, that's what it is doing, yes. Is anybody ready to run lamps?
I already did. It worked for me.
On this slide, we can test the container. Chrun set env. It's one of those ones where we need the environment variables turned on. Lamps.sqfs. Dash dash is just the Linux terminology for I'm done processing chrun arguments. /run script, that's the run script we put in the container. MPI run, which is also in the container. LMP, which is also in the container. And then -h is just a test. It's does it work? And so if this command prints out, here's how you use lamps, then you know you have correctly built a GPU-ready image. And if the GPU-ready image didn't work for you, but you were still able to get to a GPU node, you can use the backup copy located here in the training directory. If you want to see lamps do the thing, we just need a couple more files. So from the training directory, I have copied a benchmark that Lamps designed. The Lamps community does this benchmark. LJ stands for Leonard Jones. It's basically billiard balls bouncing off of each other. So we have a in.lj.txt. We need to copy that into your local space. And we have a benchmark.sh, which is the actual command that we need to run to launch Lamps and do the simulation. And we need to copy that into the local directory, the Scratch area. Once you've copied both of those, then all on one line, we can run Lamps. And we need to provide the additional arguments to mount the Scratch space. Now, in this particular example, we don't have to mount the Scratch space to a space that is named Scratch. And this container has an area named host pwd that we can conveniently use for this purpose. So we're just conveniently using host pwd to mount your current working directory. It's slightly easier because this directory already exists in the container. So it's chrun --set env -b, and we're mounting your current working directory /host pwd. So that's outside the container. Your current directory becomes inside the container host pwd. And then -c means have your starting working directory be this host pwd. The image name is lamps.sqfs. -- means we're done processing chrun arguments. And now we're going to execute commands in the container. We're going to execute run script bash benchmark.sh. This is a shell file, so we need bash to read it to execute it. And if you successfully do that, you should see lamps have a bunch of output. It should say things like using one GPU, having an MPI grid, making a bunch of atoms. Here's some performance stats. There's a lot of output if it works correctly. Did anyone have a question about what any of the commands on this line means, or was anyone able to successfully execute this all on one line and get lamps to produce a lot of output? We have one person who said it worked well. Okay, very good. Did lamps tell you that it used a GPU? If you scroll up, you should see one of the first things it says is using one GPU. So with these GPU ready images, it does take a little bit of work to get them to do the thing. But it's still a lot less work than installing lamps. Anyone here ever tried to install lamps from scratch? It's not easy. It's a real pain. So having a build of lamps that's functional is a big step up, even if you have to learn how to do some containers things. Okay, so I have a request to go over this long command again. Chrun means we're going to launch a process. Setenv means we're going to set the environment variables that are in the image. B means we're going to mount a directory from the physical file system into the container. We're going to mount the print working directory, which is just short for your current working directory, from outside the container. Colon means a new name inside the container, and inside the container it will be named host_pwd. That's simply a directory that was conveniently provided for this purpose. Then we have -c, which means have your starting working directory be this one, please. And we switch to host_pwd. And that way, these two files we previously copied will be in our current working directory in the container because they've been mounted. Then we have the name of the image, lamps.sqfs. Then we have --, which is just a standard Linux way of saying I'm done with chrun arguments. No more chrun arguments. So everything that follows is a command to run in the container. So the command we're running is /runscript. Runscript is a wrapper around the lamps executable that sets some additional environment variables. NVIDIA always does this. NVIDIA always has a run script to set some additional environment variables. I wish setenv would do them, but it doesn't do them all. It misses a few, and the few that it misses are here in the run script. Then benchmark.sh contains the actual lamps command to do this benchmark. It is a shell script, so we have to launch it with bash benchmark.sh. That's easier than making it into an executable. You can make it into an executable, but it's not worth it. It's easier to just do it like this, where bash is the executable and benchmark is simply a list of commands in shell language. We are actually a bit over time, so unless there are, I would prefer to take general questions now rather than questions about lamps. We're actually done looking at lamps. You can see the next thing in the slide is the Clara Parabricks example. We do not have time to do that one live, but it is available. So we're going to skip past Clara Parabricks and show the acknowledgments slide. This work was supported by the National Science Foundation. We have some award numbers here. We have the ACES Award. That's the same name as the cluster, by the way. Accelerating Computing for Emerging Sciences. That's NSF gave us the money to buy all these nice GPUs like the H100 we just demonstrated. We have SWEETER. SWEETER is our Southwest expertise in expanding training, education, and research. So they're the ones who paid for training exercises like the one that you've just taken. We have FASTER. FASTER is the other cluster that we offer through Access. So, you know, some of our time comes from there as well. I should also thank the staff and students at Texas A&M HPRC. A lot of people came together to make this coursework. And finally, I'd like to acknowledge the ACES CSET pilot program, which awarded a Tier 2 grant for this work. So that means someone is going to get their travel expenses paid to go visit the conference of their choice. If you're curious, it's me. I'm going to go visit SC23 in Denver. That's the award that they provide for giving these materials to the Access community. That's you. You're the Access community. So I'd like to thank you for participating in this short course and helping to make the pilot program possible. So here's our how to ask for help slide with our email address. I'm just going to leave this on the screen for a while, but basically, I will remain here to answer your questions for as long as you need to. I've got nowhere to be. So if you have questions, you can ask. I'll do my best, or I'll refer you to people I think can help you more.